Hello, in this video we are going to talk about Unit 7, Topic 7.5, which is simple and physical pendulums. First, we are going to define a physical pendulum. So, a physical pendulum is a rigid body that undergoes oscillation about a fixed point. So, for example, if you have, let's say, that's the rigid body and it's going to oscillate. So we have here, it's going to be, that's the center of mass. And let's say I have here a point, so that's the point of oscillation. So we can draw it like this, and we'll have an angle theta here, the angle. We are going to have here a distance d, and it's going to have a length L, as you know. And we said this is the center of mass, and this is going to be the fixed point. Now, again here for theta, we are going to say that sine of theta is going to be equal to theta in radians, and radians for small angle approximations. So we'll start our derivations. For small amplitude, we already know that we can find that for small amplitudes. So I have a small theta. We can find that the period of a physical pendulum will be equal to 2 pi square root of I over mg times d. Okay, from that we can, right now we are going to derive the torque. We know that the torque, here we have the force, it's mg, it has a mass m times g multiplied by the length L. Now, we on the other side, what is L? L is going to be d times sine of theta, but sine of theta we said is equal to theta, so the torque will be equal to mg times d times theta. Now we also know that the torque is equal to I times alpha. And similar for oscillations and simple harmonic motion, we know that the force is going to be in the opposite direction, so we need to put the minus sign. From that, we can put that those two, they are equal. We'll see that I alpha will be equal to minus mg d multiplied by theta. So alpha will be equal to minus mg d theta over I. Now, remember from what we said before, again here alpha is d theta, d squared theta by dt squared. So we can, if we replace that, we'll get d squared theta by dt squared will be equal to minus mg d over I multiplied by theta. So that's an important equation for us, and this is the other important one. Now, if you remember, if you want to derive that T physical that we spoke about before, that's alpha equals to, as we did before, minus omega squared theta. So in that case, omega squared will be equal to mg d over I. So omega will be equal to mgd over I, but under the square root, and we have t equals 2 pi over omega, and if I replace it, I will go back to the previous equation that we got above. So 2 pi square root of I over mgd. So again, the derivation is just the same as we did before the pendulum and for the spring. Now, a simple information, the simple pendulum is a special case of the physical pendulum. Why? For the simple pendulum, I is equal to m times d squared. If I replace that above, we get t equals 2 pi square root of md squared over mgd, which will be t equals to 2 pi square root of square root of d over g. Instead of d is the same as L, which is the length of the pendulum or the rope connecting the pendulum. The second one that we'll talk about is the torsion pendulum. So torsion pendulum is a case. Torsion pendulum is a case of simple harmonic motion where the torque or the restoring torque. So before we had the force, right now here we have the torque is proportional to angular displacement. So before we got the restoring force and the displacement, here we have the torque and angular displacement. So the torque will be equal to minus kappa multiplied by theta. That's a constant for each pendulum. We call it the torsion constant. Okay, so and we already know that the torque is equal to I times alpha. So again, we can equate them. I alpha equals to minus kappa multiplied by theta or d theta. So alpha equals to minus kappa over I theta, and this one it will be d squared theta by dt squared equals to minus kappa over I theta. Now, in many cases, instead of theta, they write it as the change in angle. Okay, keep that equation in your mind. Now, if you look at this one, this is the same as we have done before. So omega squared equals to kappa over I. And from that, we can say T equals 2 pi square root of I over kappa. Again, here omega, if you forgot, it's kappa over I, the square root of it. So that's the equation of the period of a torsion pendulum, I over kappa. As you see, all of them, they undergo the same derivation, but different letter, different names. That's it for 7.5.